In this video, number 11 for the TEAS, preparation for the TEAS exam, I want to give you some tools to use for balancing chemical equations. Okay, so a chemical equation is going to be set up in such a fashion that on your left-hand side, there will be reactants. That is, elements, compounds, even ions sometimes, that are added together to produce, and we put an arrow in there, to produce products. That's the format for a chemical equation. All right, this equation is balanced. How do we know that? We know that because you have the same number of element symbols on the reactant side as you do on the product side. So if we look here, we've got three oxygen molecules with 2 atoms each, which means 6 atoms. And then we have another oxygen with this ethanol group, so that's 7 oxygens. We look on the other side, we have 2 times 4 oxygens plus 3 times 1, which is 7. That's balanced for oxygen, and we do the same thing for the other elements to be sure that they are all the same number of atoms of each element on both sides of the equation. That signifies a balanced equation. Now, this can be interpreted in one of 2 ways. We can say that we have 1 molecule of ethanol, C2H5OH, plus 3 molecules of oxygen yields 2 molecules of carbon dioxide plus 3 molecules of water. Or we can say we actually have 1 mole, or 6.022 times 10 to the 23rd molecules of ethanol plus 3 moles of oxygen yields 2 moles of carbon dioxide plus 3 moles of water. Now, that latter interpretation is much more useful because we have a way of equating moles of individual compounds with their mass. And that's much more useful than looking at it in terms of atoms and moles, atoms and molecules, excuse me. Okay. So when we have a balanced equation, the ratio of reactants to products is based upon the coefficients, the numbers that precede each one of the terms. All right? So if we go back, we find that C2H5OH has no explicit coefficient. That means the coefficient is 1. Oxygen has a coefficient of 3, carbon dioxide has a coefficient of 2, and water has a coefficient of 3. Now, another rule that goes with balancing these equations is once you write these terms correctly, this is ethanol, this is oxygen, this is carbon dioxide, and this is water, you cannot touch these subscripts to balance the equation. You have to balance by using coefficients. Okay. The other thing that we're saying with this balanced equation is that this is 100% efficiency. In other words, if we put something in on the reactant side, and we have enough of the reactants available, we produce all of it into products. Now, as a practical matter, that never happens, but that's our starting point. Now, if we need to if we need to convert so many moles of a reactant to so many moles of a product, then we use the coefficients to build a conversion factor. And I'll show you how that's done in just a minute. Right, when we say amount, we usually mean numbers of moles, counting numbers. We don't balance equations based on mass. We balance them based on numbers of atoms and numbers of molecules. So if you're given a mass of reactant and a mass of another reactant, you cannot determine the outcome of that reaction until you convert those masses into moles. Okay, so these are the steps for writing and balancing an equation. I put these up here so that you'll have the steps listed, but in reality, a demonstration works a lot better. I will make this point. In most chemistry textbooks, at least in the past, they're coming around. The authors will simply say, balance the equation by inspection. And that is essentially the authors evading the problem of showing you how to balance equations. That's what I'm going to do in subsequent slides, is show you how to balance these equations in a methodical way so that you can be more successful, at least with the simpler equations. There are some chemical equations that are really bears to balance, and some of those I won't even tackle. Some of them you actually need a computer program to help you. But the method I'm going to show you will work for 3/4 of the equations. Right. These are helpful hints. In other words, things that will help you smooth the process. And they're not going to mean a lot right now, but I put them up here so that you'll have a record of them, and I'll point them out as we go. Okay, so here's the first example. I think I'm going to save this example and give you a different example, and we'll come back to this one. So let's say I want to burn methane, right? You have natural gas coming into your house and you light your stove, and this is the reaction that occurs. So we have methane. That's a gas. And we want to add oxygen to it, which is a gas, and it produces carbon dioxide and water. Okay? So we have written the compounds correctly. Right? We have methane, oxygen, diatomic element, carbon dioxide, and water. The procedure I'm going to show you, I call it my budget method. So we assess where we start. In other words, what do we have to begin with? So you take each of the elements and list them down this side. We have carbon, we have hydrogen, and we have oxygen. That's all the elements that are in this equation. And then we assess how many of each. So we have 1 carbon, we have 4 hydrogens, and we have 2 oxygen atoms. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay? Now, the first trick or the first hint that I find very useful is if you have one of your elements on either side of the equation is in its element form. In other words, there are no other elements combined with it, like oxygen. Save that one to last, because when you put a coefficient in front of that one, it only changes the oxygen. So we're going to save oxygen till last. And we're going to look at carbon's already balanced temporarily. So we're going to go to hydrogen. 4 hydrogens here. We need 4 hydrogens on this side. Coefficient of 2. 2 times 2 is 4 hydrogens. That also changes the oxygens. 2 oxygens and 2 is 4 oxygens. Okay? Now, since the carbon's still balanced, the hydrogens are balanced, we can go to our oxygen, the very last one, and we just need a 2 in front of that one. 2 times 2 is 4. And with this method, you can see at a glance whether or not you have balanced the equation. 1, 4, and 4. That equation is balanced. Now, for this equation that's on the slide, there's another hint that's I find very useful. If your compounds are written with polyatomic ions, this is NH4. It's a single unit with a +1 charge. And phosphate is a single unit with a 3- charge. That's why we have 3 positives to balance 1 with 3 negatives. So NH4 taken 3 times, PO4 is the correct way to write that compound. Calcium is a 2+ ion. It's an alkaline earth with a 2+ charge. Chlorine is a halogen with a -1 charge. So we need 2 chlorines to make that calcium balance. On this side, we have 2+ charge with calcium and a 3- charge with phosphate. If we have 2 phosphates, that gives us a -6, and 3 calciums, that gives us a +6. Total, that balances. So if you have a polyatomic ion that does not break apart in the reaction, sometimes they do that, but if it stays ammonium on both sides, NH4, NH4, PO4, PO4, then you can use those as balancing units. It really simplifies the process. So I left the charges off, and that 4 should be a subscript. So we've got an ammonium, we got a phosphate, we got a calcium, and a chlorine. The initial tally is what? Right? Count them up. We have 3 ammonias, we have 1 phosphate, we have 1 calcium, and 2 chlorines on the reactant side. On the product side, we have 1 ammonium, we have 2 phosphates, we have 3 calciums, and 1 chlorine. So where do we start? Well, we don't have any elements that we can hold in reserve. So you just pick a place. With practice, you find out that some places work quicker than others. In this case, I'm going to start with calcium chloride. And what I'm trying to balance first is the calciums, right? We have 3 calciums on the product side. I want 3 on the reactant side, so I use a coefficient of 3. Now we do a reassessment. Okay, that changes the calcium to 3 and changes the chlorine to 6. Okay, now that we have 6 chlorines on the reactant side, we need 6 chlorines on the product side. So that's the next step. That little red 2 means that's the second step. Right? If we put a 6 in front, then we get 6 ammonia and we get 6 chlorines. The chlorines are balanced, the calcium's balanced. Now we need to go and balance the ammonia on the reactant side. So that's the next step. We'll put a 2 there. 2 times 3 is 6 ammonium. Okay. And 2 phosphates. There we go. And that equation is now balanced. We can see 6, 2, 2, 3, 3, and 6, 6. All right. Some of the other hints, you probably won't need them, so we're not going to spend a lot of time on the others. Those first two that I gave you are the most useful for beginners. To understand what constitutes a balanced equation, what we try for is the simplest whole number ratio. So if you have a properly balanced equation, like this one, right, and we can check it out. We have 5 carbons. Let's see, 2 times 2 is 4 plus 1 is 5. And we do the same thing for the rest of them. Find this is a balanced equation, and it's the smallest whole number ratio. 1, 2, 5, 2. We cannot divide by 2 and get a smaller ratio. And once the ratio is fixed, if you multiply any one of these by a factor, you have to multiply the rest of them by that same factor. We can say that this is balanced, right? We just divided by 2. Or we could say this isn't balanced, we multiplied by 2. But the preferred one is Roman numeral 2. Okay. Which of the following is true concerning balanced equations? The number of molecules is conserved. No. The number of molecules is determined by the coefficients, and that doesn't necessarily mean conservation. The coefficients tell you how much mass of each substance you have? No. Tells you the numbers of molecules and atoms that you have. Atoms are neither created nor destroyed. That's true. Right? In a chemical reaction, you do not create or destroy matter. Coefficients indicate the mass ratios? Nope. Number ratios, mole ratios. The sum of the coefficients on the reactant side equals the sum of the coefficients on the product side? No, not necessarily. No, it can be all over the place. If they are equal, then it's purely coincidental. The only one out of this group that's true is atoms are neither created nor destroyed. And these are just notes to remember. You cannot change the subscripts once your compounds are written correctly. The only way to balance the equation is with coefficients. We get the ratio of molecules, the ratio of moles of molecules. Either way, it works. Okay. Coefficients can be fractions, but we prefer whole number integers. And I think before I leave this, I want to show you one where I use an intermediate step with a fraction. So let's take the gasoline in your car's tank that you burn in your engine. That's primarily octane. So we have C8H18. And I'm going to leave the phases out for convenience. Then we have oxygen produces carbon dioxide and water. So our budget method says carbon, hydrogen, oxygen. Right? 8 carbons, 18 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay. I'm going to start with carbon. So if I put an 8 here, that's 8 carbons. And now 16 plus 1 is 17 oxygens. And now I want to balance the hydrogens. So I need 9 molecules of water to give me 18 hydrogens, but that's 9 plus 16 is 25. Okay? The only one I have left is oxygen. So how do I get 25 out of an even number? The best way to do that is an intermediate step. If I say 25 halves, that will give me 25 oxygen atoms. Now, how do I know that? Because I'm going to take half of that molecule. What's half of an O2 molecule? One oxygen times 25 is 25 oxygens. But we prefer whole number ratios. So how do I get rid of that 2? Well, now that the ratios are set, I can multiply the whole thing through by any factor I want. So I'm going to multiply through by a factor of 2. So I get a 2 here. 2 times 25 halves is 25. 2 times 8 is 16. And 2 times 9 is 18. So balanced equation with the smallest whole number ratio is 2 octanes, 25 oxygen molecules, 16 carbon dioxides, and 18 water. That's a balanced equation using the fraction trick. Okay. There's more to balancing equations when it's called for. And we could go further than that, but as far as the TEAS, preparation for the TEAS exam goes, this should be all that you will need to balance an equation.